Recording in progress.
Is it echo? Technical glitches. Is it gone? Is it okay? Right. Right. So, piggybacking off of that nice induction ceremony, it's our pleasure to welcome Dr. Michael Sherburne, one of our own, as you might have noticed. So, Dr. Sherburne received his BS in electrical engineering from Virginia Tech in 2018, where he researched pulse power technologies, developed electrical systems for dense plasma focus, which is to say a nuclear fusion device, and then completed a thesis about linear transformer drivers. He then earned his MS degree in electrical engineering at AFIT, which is Air Force Institute of Technology, back in 2020, where he explored colloidal quantum dots for both X-ray and non-destructive testing related applications. And then he earned his PhD in electrical engineering at the University of New Mexico, which makes us, him and me, alumni from the same institution. Since I got my PhD from New Mexico under Dr. Luke Lester, so quite a gathering of New Mexicans here. And so as part of his PhD dissertation, he investigated how nanomaterials can be used to measure free field microwaves and electro-optic sensors for RF reception, so a combination of electro-optics and RF. So Dr. Sherburne started out as an officer in the United States Air Force in 2018, where he worked as a developmental engineer officer doing cutting-edge nanotechnology and microwave research. He then transitioned to a civilian career at the Johns Hopkins University Applied Physics Lab, where he presently works as an RF and microwave design engineer, while also leading research efforts as a principal investigator. Throughout his career, he has disclosed 9 inventions and awarded 1 patent going across antenna and nanotechnology. He's a member of the Institute of Electrical and Electronics Engineers, IEEE, the Association of Old Crows, and the Society of American Military Engineers. He's actively involved in IEEE, where he presently serves as the track chair in the Sensor Systems, Signals, Processing and Interfaces track for IEEE sensors for the 2024 and 2025 conferences. So very distinguished career already. You can see a whole lot of research areas there. So without further ado, let me hand the floor to Dr. Sherburne for what promises to be a very exciting talk. Enjoy.
Hey, testing. Everybody can hear me? All good? Yes, mic's all good? On Zoom? Okay, good. Well, good afternoon, Hokies. It's great to be on Hokie soil again, just in a different location. But you got the good old logo, so it's pretty excited. But anyway, thank you so much for the introduction. Thank you, Kathleen, for the invite. It's been an honor. So today I'm going to be going over my presentation titled There and Back Again, Connecting the Disciplines Together. And I'm not going to draw on about the Lord of the Rings, but it is a very good movie. So disclaimer, everything I'm going to talk about, just my own views, has nothing to do with my employers, my previous employers. So just the usual. So yeah. And then overview, first I'm going to be talking about my roots here at Virginia Tech, my upbringing there, some internships I've done with the National Ignition Facility, the 21st Century Studies program that I did while it was at Virginia Tech, which was a transdisciplinary educational experience, which was honestly probably the most profound effect on my career. And then also I did like a interdisciplinary capstone experience. I actually did stuff with the mechanical engineering department. So I'll talk a little bit about that. And then in terms of going into how the arts helped my career. So I'm also a photographer and how this has helped as well. So just appreciate the arts. And then a little bit about the small world of Virginia Tech and my career in the Air Force, and then future technology work. So, I know everyone here has got, all sorts of interests, as a broad audience. So I'm just gonna go a little bit into some of the different works I've been working with. If you want more details, feel free to just talk to me afterwards or during questions. So don't want anyone sleeping through like a 50-minute dissertation lecture or something. No, I see that. So, yeah, my upbringing at Virginia Tech. So, yeah, as Dr. Lester said, I was completely shocked when they told me I was the outstanding senior within Tala College of Engineering. Yeah, I still don't know how, but I think a little bit was from just all the involvement I did across the campus throughout my years there. So I just put some highlights up here. As you know, I was commissioned as a second lieutenant in the Air Force upon graduation. That was in 2018. I actually graduated from the Corps in 2017. The reason why it was 5 years was just we did like 180 credit hours in the ECE department with all the other stuff. So that's why it's a 5-year program. Yeah. There we go. And again, also like relationships for life. So, the biggest thing, when you're at Virginia Tech, and especially why you want to come to BT, is really the networking, all the amazing professorships here, and also research opportunities, people, future spouses, all that good stuff. So actually, I had my exit buddy at graduation, the awesome Virginia Malloy. So she's presently my wife, and yeah, well, still currently and everything else. Yeah, for life. Okay. One of my best friends, Joe Tony, here is messing with me, but it's all good. He was also in the Corps Cadets with me. And then in terms of relationships for life as well, to the top left, we have Lieutenant Adam Summers, who I still work with to this day. We just keep on merging with our career paths. So he did an naval route. He's working as officer in the Navy. We actually were in elementary school together and all the way through high school and everything. So yeah, just, it's a small world that you still keep bumping into each other. Same with the commissioning class here. We have Captain Noel Guadalupe, Captain Katie Wheeler, and Austin Shumate, and Captain Luke Bergeron. Captain Luke Bergeron, Dr. Lester, one of the other very few double E's with me. Same with Captain JD Veracruz. So I still stay in touch with everybody here and still work with them. Even though I'm not in uniform anymore, I'm still working with a lot of mission-oriented things. And then the bottom left with my Omicron Delta Kappa circle when I was president of the circle back at BT. So that was a great experience as well, where we were working with student leaders from all across all these different organizations on campus, and also advising the vice president of student affairs. So yeah, just a quick intro on that. And then with all the excellent research opportunities at Virginia Tech, I was able to work with Dr. Colin Adams at Space at Virginia Tech and the nuclear fusion program there. And that actually led to an internship opportunity through the RTC programs at Lawrence Livermore National Laboratory. You might have all heard this on the national news when they made big news last year that they achieved ignition, which is part of the National Ignition Facility. And what ignition really is about is you're getting a lot more energy out than you're putting in from a nuclear fusion reaction. So when they finally achieve that, that's massive. Now they can only go up from there. Eventually that can lead to what everyone's claiming is unlimited energy. So I entered there in 2016. I worked on capacitor diagnostic systems, and it was really neat. So basically just think of a stick that you just tap a capacitor with, and you can check the health of that capacitor. And this facility is massive. We're talking like football fields of just power electronics and pulse power, and it's huge. And you can imagine with these capacitors being, yay big, and you got thousands of them, you have to make sure they're all in good health when you're doing every shot. And they have to keep up the schedule because every single shot leads it closer to these new scientific discoveries. So beforehand, it was usually you take the cap and you pull it out, and then you have to like physically measure it and put it back in. That requires a lot of procedures versus, say, in this case, they have to do much less with poking it with a stick. And there's other options as well for sensing, but that was the one thing I was assisting with. So that was a really cool experience. So, even working on the capacitor level, all these things have to work with each other in order to make this whole system function. So, and Star Trek was filmed here. That's why I was with a coworker. We were wearing Star Trek's uniforms for opening night of the third movie of the trilogy. So that was super cool. And you can still see some of the Hollywood sets there, because the reactor in Star Trek Into Darkness from the second movie was also filmed there. So yeah, that was a great experience. So, but anyway, that's also because just the excellent research we have at BT. So be able to do these experiences. And then I did a transdisciplinary education early on my sophomore year. It's called the 21st Century Studies Program by Dr. Robert Siegel. And you had a group from all over the university, honors, not honors, architecture, just every type of discipline possible, which made it a really great group to work with and learn from, and doing research towards societal issues from around the world. And we also got to do a capstone project. So for mine, I looked at water issues and how do we address those. And I specifically did field research in Sri Lanka when we were there, and I was there for a couple months doing that. That was quite an experience. I was actually by myself when I was doing this, and just working with a local NGO called the Sarvodiya Ramadana Movement of Sri Lanka. And yeah, it was quite an experience trying to communicate with various language barriers and all that, but still came out alive and everything, so it's all good. But it was actually excellent work there, and honestly, the NGO I was working with was excellent. They handled everything very well. So yeah, we were initially in Morocco, we went to Turkey, and then we went to Sri Lanka. So it was an excellent study abroad program, took the whole summer, and then we continued to have seminars and lectures for semesters afterwards. So now, why was Sri Lanka part of our curriculum? It's kind of like we're just over here from all over the other places of the world. It's actually quite a great case study for quite a few things that are presently happening in today's society as well. Not to mention, still very excellent culture. It was really lovely community there. But what we're looking at initially was the formation of, say, modern terrorism as we know it. So, for instance, there was unfortunately a really bloody civil war that happened decades ago, and within that civil war came the Tamil Tigers. Some of you might have heard of them, but if you haven't, they're the ones that actually brought to mainstream what modern day terrorism looks like, say, for instance, suicide bombings and the such. And we were then studying the mechanisms that led up to this insurgency in order to help us understand how could one anticipate an insurgency that could occur and prevent that in the future. And part of that within the Sri Lanka context is, for instance, how did colonialism lead to a civil war and terror in the country? So that legacy that the colonialism had on the country, how did that lead to a fracturing of ethnic groups and that fighting against each other and such? And we're still dealing with all that even to this day with many parallel cases. And in addition, the geopolitical importance of Sri Lanka to the world. So, for instance, right, so you have India, and then you have Sri Lanka, and then all the world shipping lanes are around to that. So it's definitely a really good country to study for sure, and something to learn with and hopefully prevent repeats of the history happening in the future. And then when I was looking at clean water, why was I interested with that and why did I choose that, especially in EE? Which, electrical engineering, we do lots of sensors towards measuring water quality. So you can still do anything really as EE. Or computer engineering or CS, we do all those things here. So I was looking at that because of the implications of access to clean water. For instance, for Syria, what led to the civil war, and not the only cause, of course, but it helped with that powder keg, was the drought of the Euphrates River a couple decades ago. And as that drought continued, of course, you can't live by the river if your farmlands are drying up. That caused everyone to start going to cities. That caused the buildup of issues occurring. And then that eventually bubbled up, turned into a civil war. And unfortunately, we're seeing these things happen all across the world when water access, and specifically clean water, is not made available. So that's why I had interest with that, and why I still have interest with water availability to this day. And then in terms of transdisciplinary education aspect, which I encourage everyone to do if you can. I know in grad school, maybe you're a little more focused and can't just go right to the liberal arts side too, but if you can, especially for the undergrads. Interesting. Okay. So This projector doesn't like me talking about it, but anyway, you're doing research right across not just your other engineering fields, but across, say, business, across architecture, sociology, psychology, and all those things. And then you're doing that also in terms of your research with other universities from across the world. So when we're going to Morocco and Turkey and Sri Lanka, we actually went to their academic institutions and we talked about societal issues. And then also exchanging of information about how we can improve upon issues that are happening across the world, whether it be water access or better access to air conditioning, et cetera, et cetera. So. And then in terms of my interdisciplinary capstone projects, I did this in the mechanical engineering department. I didn't have a say in what to do. Just a bunch of my friends came up and were like, we need you to help us with this project. And these are all my colleagues as well from the nuclear fusion aspect at Space at VT. And then they had this crazy idea of making a dense plasma focus. So what dense plasma focus is, you can see it here. It looks like a Gatling gun, but instead it's jetting out plasma. And that plasma comes out, and then it comes back in, and it's like a jellyfish. It like goes in. And when that comes back in, that creates this massive amount of energy and can cause fusion to occur. For instance, we're looking at deuterium type of fusion. And the purpose of this wasn't for making clean energy. It was actually for nuclear forensics for the nuclear engineering program at Virginia Tech. And what happens there is with that nuclear fusion reaction, you can create a large amount of neutrons. So you can make a neutron source, which then can be used for something called neutron activation analysis. So you can use that to actually gauge the elemental composition of whatever is being affected. So you make something temporarily radioactive, and you can look at the decays from it. So to do that, you need a neutron source. So this is a relatively inexpensive way of doing that. And it was a great experience because I was trying to learn the lingo of the mechanical engineering students and the professors about like the electrical engineering terms. And there's sometimes we're talking over each other, and then learning how to get on the same page. So very great experience, and it was a great team. So we also won an innovation award with that, and it makes for pretty photos. So I mean, he doesn't like plasma, so. Right, so that's why we have like boron nitride shielding. So yeah, we had to do all the EHS stuff, and I was actually more concerned about shocking myself. I mean, you're talking 25,000 volts, 90,000 amps. Stored in there. Correct, all this pink stuff right here. So that helps to shield out all the neutrons. Right. Oh well. Yeah. When we're running this, we'd put everything over. But when you're showcasing it, you can't just show people a box. But yeah. Yeah. That's actually just helium, so it can't do anything. That's how we were able to take it. With the deuterium, we couldn't. Yeah. But not having the photo doesn't really sell things. So yeah. So and then going about photos, so I did photography for a while, still do, sometimes in other ways through my engineering career. And I actually did outdoor portrait photography. So you actually might know this amazing woman here, Captain Noelle Guadalupe. So she's actually kicking butt in the Space Force right now, one of the first officers to commission from there, because we all have to transfer because it just started. And I actually was able to use my photography skills as well to say take photos of the work I was working on. For instance, the capstone project. So this is a fiber optic transceiver unit in order to give us a isolation from the pulse power. I remember when I was pitching this at the design review for mechanical engineering department, they're like, where did you get this on Amazon? I was like, oh, we made this. But when you have a really nice photo, it actually helps to legitimize what you're working on. Yeah, still laugh about that. But it's great. And I still apply the photography skills, for instance, whether it be with photography, for instance, rendering SolidWorks, when you can do real life rendering of your tools and products and such. And even if you can't do any of that, as long as you have appreciation of the arts and know the higher illustrator or whoever, that can help a lot for your pitches and presentations. So yeah. And then it is a small world. Some of you might know Alex McDonald here. So he was actually one of the year groups behind me or after me. I can't remember right now. But anyway, so he's younger than me. And he took over the dense plasma focus project. And he's actually now doing his PhD at University of New Mexico. And he's doing it under Dr. Jane Lear, who was my PhD qualifying committee member, who also knew, and everyone knows Dr. Lester here because he worked at UNM a long time ago, back in the day. And then my advisor is Dr. Idil Shamaluglu, and how I got in touch with him was actually through Dr. Colin Adams, because he worked with Dr. Shamaluglu as well. And that relationship actually led to go into the PhD program later on. So from undergrad all the way to my graduate career. So just showing you, it's a really small world out there, and everyone you know, eventually they're going to come back to your field. So it's important to mentor the next generation because you're still going to be working with them. So the United States Air Force, I wish I had more photos of it, but here's some notable photos. So the photo here on my right side is my farewell lunch with all my military friends for my last unit in Kirtland Air Force Base. So a great group of folks. I was working on high power electromagnetic devices, and I'll just leave that there, not to go too much detail, but definitely a really good experience. When I started out in the Air Force, they had me go to the Air Force Institute of Technology for my master's degree program. So keep in mind, I was doing nuclear fusion, pulse power stuff, and then the Air Force like, oh no, you're going to be doing semiconductors. So fairly different on micro electromechanical systems. But it was all great. Dr. Hingi Chandrahalam was our professor, and he taught us a lot. And I still work with him to this day. And then at AFIT is where I got into nanotechnology. So I wanted to be involved with nuclear physics, and then that's where I got involved with doing my electives at AFIT with nuclear physics and nuclear engineering, and then I combined that with my semiconductor program and use that to do X-ray detection. So I looked into it. We needed a very fast X-ray detector, and colloquium dots are a potential solution to that with a really fast fluorescent decay time compared to traditional phosphors. So I won't say any other words from there, just standard phosphorescence and fluorescence, so the decay of light. And this other photo right here, so after the Air Force, and I'll go back on some other Air Force stuff, but I really want to bring this part up too. So I was surprised to find out I was then awarded a Air and Space Commendation Medal, and I was already at the Johns Hopkins University Applied Physics Laboratory for that. So some of you may know, or may soon know, or someday, when you're going from the military and you're separating, and then you're now on your own civilian world, it can get very lonely out there. So you try to find your battle buddy, as well as, for instance, the veteran community, because it's really tough. I mean, unless you have served, it's really tough to understand what we've all gone through. So my battle buddy at Johns Hopkins was actually in this room, Elvis Nguyen. So yeah, so he's a Marine Corps vet. So I actually had him. He helped me out with the presentation of my commendation medal when I was there. So thanks, bud. Yeah. But yeah, but one thing that you might not think about with a military career was actually like not even the technology or what we were even working on, was actually just the education training that we received. So other than the graduate degree programs that I was able to do throughout the Air Force, it was actually the acquisition training that we received that has been paying dividends now in my career. So I was a developmental engineering officer. We had to learn about program management, contract management, and all those sorts of things, or at least have a good understanding about it. And even laboratory management. So for instance, when you're writing proposals and Gantt charts, snake charts, and all those things, I'm actively using that right now at my present job at Johns Hopkins Applied Physics Laboratory. So, I know for a lot of folks that are in the service presently may not appreciate any of that, but if you've never seen any of that before when you're writing your first proposal and you got like a couple weeks to write it up, it helps to have that to lean on and do that quickly versus trying to understand every little term, like what's the FAR, you know? So, yeah. And then this is a rare moment of Dr. Gil Shimalulu smiling and the voting ceremony. All those people I've actually bumped into at conferences prior, and they'll carry throughout your whole career. And MATLAB may not be the most favorite thing for babies. So this is my son Holden. This is after doing hours of MATLAB plots for a peer review publication. Yeah, he'll use MATLAB. And then going on to the IEEE Census conferences, I was honored to have been invited for 2 of my peer review publications last year in Vienna, Austria, along with being a session chair for the IEEE Census community, where I talked about, for one of my papers, looking at calibration of electro-optic sensors for radio frequency sensing, along with another paper looking to another calibration methodology for gigahertz transverse electromagnetic cells. Basically, it's like a fancy RF shaper to do RF measurements on, whether it's for in standards for the FCC, but I'm focused on electro-optic RF sensors, not chambers, for this talk. Metal. And you know, they're very great, but they also have a lot of drawbacks, especially when it comes to, say, doing field measurements. You're doing these for fields, there's a lot of other things you have to consider. So by large electric field, I mean fields that are greater than, say, kilovolt per meter. First, in terms of the sensors that are available for this, I'm just going to bring up one example. This is a DDOT antenna. So this is a wideband high electric field sensor. Can go anywhere from above 0 hertz to right now they're around 10 gigahertz, and they can measure the entire spectra at once from a pulse. And they're really great, but the issue is they're still relatively large size, especially if you want to put into something small. And they also have to have something called a balun in free field, which is another big metal box that you have to have that can potentially perturb your measurements. And by perturb, I mean when the RF goes into a boundary or a structure, it can actually scatter, and that scatter can come back right onto your dipole and then influence your measurements. So are you really measuring a voltmeter, or is it actually, let's say, 3 voltmeters or something else? Like, you don't know. You have to do lots of calibrations. And then that also goes into, say, bandwidth. When it comes to metal antennas, it's all about geometry for what frequency ranges they can handle and to what frequencies they can work with. And in addition, how you measure from the antenna. So you have to use traditional coaxial cables, which can be influenced by the environment, especially when you're outside. So then in comes electro-optic sensors, which they're finally starting to get to the point of plug and play from decades of research. This is a Seiko Geekin electro-optic sensor. Sensor right here, this is the controller. And the neat thing about electro-optics is they contain very minimal amounts of metal, and they're also relatively small size. So you're going from, let's say, maybe around a foot length of a sensor to now about the size of your average human pinky when you're working with these devices. In addition, some of these can come in a certain package where they can actually measure 3 orthogonal axes at once. So traditional metal antennas, you would have to take the antenna and like flip it in 3 different directions in the same spot. But now you can do this with a single electro-optic probe and measure all 3 axes, which is important because unless you have a perfect plane wave, which is only in textbooks usually, things scatter around, and maybe you want to look at the total field that's coming from all directions. And that's what you can do with these devices. They also do have promise for higher bandwidth. So some of the commercial ones right now, they're 10 gigahertz. Some can be pushed towards 20 gigahertz, and there's actually promises of going further than that. And they can even measure high electric fields. So a metal antenna obviously can only measure to such a degree. If you need to get to megavolt meters, that can become an issue. That's where this one electro-optic probe from Captios is claims to go over megavolt meters. And there has been some work that has been done with that. So, you know, it depends on the tool for the job. There's a different array of these electro-optic probes. And something I've noticed too is there a better way to term these sensors? So for instance, you know, you might have what they call Mach-Zehnder interferometry-based electro-optic probes. There could be Faraday rotation types of probes. All these different ways of taking the RF field and then modulating the optical field and then reading that out. That made the lit review a little bit difficult. So then that's where I went ahead. I actually consulted with the National Institute of Standards and Technology, NIST, to talk about maybe a better term for this. And again, this is just more of a consultation. And what we came out with was EORF. So just kind of a play with EOIR, which is, you know, more camera imaging and such, but in terms of RF. And it means electro-optic sensors for radio frequency reception. I went ahead and IEEE sensors showcased this term. Yeah, I'm hoping everyone in the community can start using this term when referring to the overall field of EORF. And then in terms of the research I was doing for the paper, I was looking at how can we take these electro-optic probes and use them in an outdoor field environment. After considering all the different things that could happen and how could we control them, the hardest one is ambient temperature. If the actual temperature of that sensor changes, it's going to be influence your measurement no matter what you do. And therefore, looked into how can we calibrate that temperature measurement. And that's actually a non-trivial question. So if you want to measure the temperature response of these radio frequency probes, and for instance, a RF chamber. In this case, I used a very small gigahertz transverse electromagnetic cell that was actually donated by Dr. Jane Lear, and I was working on it. So again, going back to this whole small world part here. What I've noticed was when you're lowering the temperature and increasing it with everything inside, everything is changing, not just your sensor, but your chamber itself. So that can create two linear responses. From theory, we know that when in terms of the sensor, it's a lithium niobate crystal, and these crystals are supposed to have a linear change to a applied electric field. But in this case, it turned into this parabolic mess. And what we determined was the GTEM cell that was being used has a linear change, and then the EO probes also have a linear change. So that's where I went in and used some training I had with statistics. So with this one method called design of experiments, which I definitely encourage everyone to learn, is where you can take different factors. So I'm taking the factor of the electric field, I'm also taking the factor of the temperature, and then I can look at the interaction between the factors. Ideally, they should be independent from one another, but they were intertwined because of the mixture happening with the GTEM cell changing and the EO probe changing. And so that's where I went ahead and developed a methodology to iteratively lower that interaction factor with the calibration factor for my data. And from there, I can have reasonable certainty that at the end of it, I have a useful calibration line. Now, just to check, we did these 3 points for the calibration. And then we did 2 more midpoints just to see how that fits with the calibration curve. And what you'll notice here, the bottom line, that's a large electric field level. In this case, around 15 kilovolts per meter. The top one is a low electric field level. And you'll notice how this one better correlates with its trend. The higher one is much further off. And that actually makes a lot of sense. And this leads to another novel use of this tool, is you can use this to probe the operating point, is what we say in this field of these probes. In terms of how it takes that RF, for some of you know about like MOSFET amplifiers, and you have this, gain. And depending on what voltage you apply, that, one line, then that makes it a larger voltage coming out. So that's how you have like an amplifier, for instance. That's kind of what you're doing here. There's a sinusoid, and you're working on the linear region of that sinusoid. And what can move that sinusoid is basically the electric field. So you're moving up and down. And if the electric field's too high, you can actually start to go into a nonlinear regime, which is basically where your measurements will not be valid. In addition, temperature will also shift that. So if you're shifting with temperature and you're also shifting with a larger electric field, you'll actually go into a nonlinear regime. And that will give you additional errors. as we're seeing here. So for future work, you can actually use this to then do additional levels, and then you can potentially go ahead and figure out the operating points using this methodology. Yeah. And then, oh man, I love talking about quantum dots. So Joe's just laughing here. I talk to his ear off like hours every day about these things. So thanks for listening to all that. Yeah. So as you heard, quantum dots, they were recently awarded the Nobel Prize in Chemistry for the ones that invented it last year, which has been great for our community. They can be used for all sorts of sensing materials and other applications. In terms of what I've been doing with them, beyond just say X-ray detection, I've also looked at strain sensing. And I was doing this while I was in the Air Force, and it led to some other cool opportunities I'll explain soon. But in terms of strain sensing, we can take these materials, we can apply them in a binder. So basically a organic polymer. So let's say, like silicone from like a caulk gun, and then mix that up with the nanomaterials and then apply that to a surface. Now, previously, researchers have been looking at this with a very smooth surface on the piece of metal, which is great for a physics experiment, but when you're trying to eventually operationalize it, that could just flake off. That was our concern. So when I was at the Air Force Institute of Technology, I paired up with students from the aerospace department, and I tag teamed with some other work they're doing with dog bones. Basically, little samples that you can use to strain and measure the mechanical properties of your material. And what we did was we added a coating of solvay, so basically a primer that they use on aircraft to help paint stick to it. And that adds just a little bit of a rough surface to better adhere to, let's say, you want to add like this nanocomposite paint. And we did that and did a little bit of experiment at AFIT. And this is a cool thing. This was actually a whole site experiment from a master's degree that became much larger. And so it's become another area of my research in my present career. But you can go ahead and this is a 0-dimensional strain test, excite all of the material, and then you can measure the spectra end to a spectrometer. And then from there, we had the spectra, we measured from the peak, and then we measured a little bit to the side. And looking at the relative measurement at that time, we're able to then correlate that to the stress strain curve. So you can see these specs here, and then this is in reference to the mechanical strain. Now, the reference to the mechanical strain is just on the edges, and you're pulling on it, and that's all it's measuring. We were measuring this right in the middle of this dog bone. So we also looked at a digital imaging correlation measurement to see how that was changing compared to what the mechanical sensor was measuring. And we were then looking at how this technique can actually look at what is on locally. So the next steps, of course, would be to look at a rastering type of system to do a 2D measurement, which has been applied in other materials before. So by doing it with this, that'd be cool. Imagine like in real time, you can have a camera and then just have a strain map of what you're looking at. So that'd be great for non-destructive evaluation of our aircraft infrastructure and make that a whole lot faster than present methods. So potentially could save a whole lot of lives as well. So yeah, so it's pretty cool work. And then I'll go to a whole other area. There we go. So I've also been looking at magnetite nanocrystals. So these are magnetic particles. So everyone's aware about magnetics, right? So you got like permanent magnets that you use to, I don't know, hang your photos on your refrigerator or whatever else, I don't know, for fun stuff, maybe for motors and such. And then you also have ferromagnetics. So for instance, whenever you plug your laptops in, well, they got a lot smaller now, but back in the old days, when they were like large, heavy converters from your wall to your laptop, there's transformers in there. So those are what we call soft magnetics. And then there's a new type of magnetics out there called super paramagnetic materials, which is where these magnetite nanocrystals come into play. If you shrink the domains so small, these magnetic domains, they can actually experience a point to where they'll just instantly flip with very, very little losses, practically negligible. So that's where it looks like in a magnetism, we call it a BH curve. Essentially, it's just if I am magnetizing this material with a magnetic field, how well do the magnetic domains align to that magnetic field? if they just easily align with it, and there's not much, for instance, trying to keep this broad because no, not everyone likes electromagnetics across the double E community. But for instance, when the domains are going, the ease of moving that domain with the most minimal amount of force. So the more force it takes to move that domain, the more energy that's going to be used up from that applied magnetic field. And when you're doing that in a positive motion, let's say for like an AC field, like 60 hertz from your wall outlet, when you're going forward and backwards, it can create this loop where it has an area associated with it. And in that area, that's energy loss. So for every cycle, you're losing energy, and that makes inefficiencies. So the goal for making, say, more efficient power electronics or other devices is to make this area as small as possible. And that's superparamagnetism can come to play. So of course, the first steps is modeling, doing physics and doing math. I know everyone here loves math, kind of. Yeah, so that's where the caveat is. If you were to zoom in a lot, yeah, like it's a very small amount though, like practically negligible. But I mean, of course, there's always a defect right on the particle to compared to the ideal. Now, theoretically, there should be no hysteresis, but if you were to zoom in really, really finely, then it'll be a little bit. And then of course, when you add this into a whole system, you have interactions between particles that can add a little bit more, but that should be a lot less than what a normal ferrite would be. But yeah, so in terms of the physics, you're taking what's called the Landau-Lifshitz-Gilbert equation. Basically, a lot of coefficients that help to characterize how these particles work and interact, and then do that to first principles. And I had to do a study on this. I actually published a white paper on it. And I was able to use that to help validate a new type of micromagnetics code. So when you're working with such small magnetics, there's a field of software called micromagnetics, and you can use that to help simulate these really small particles. So previously, there was object-oriented micromagnetics framework, which was built by NIST, and it was written in TCL, which is essentially I put a Lorentzian line of Fortran for how archaic it is. So I didn't really want to learn that back then, but luckily at the same time, the Imperial College London was working on something called UberMag, which was taking oomph and then applying that to Python. And that was so much easier to learn and apply. And I was in the feedback loop with the Imperial College to have updates on that would work well for modeling magnetite nanocrystals. So that was really exciting. And then of course, this is where the first principles work came in. It was just to see, okay, how close is what this model is doing to what I'm expecting? And I knew there was going to be some differences because of how finite difference time domain analysis compares to just putting numbers into an equation. So very similar responses that are in good agreement. In addition, I had to figure out a good conversion to take coefficients that are in peer review papers and apply that to UberMag. Previously, there wasn't really a conversion, so I was just getting a lot of just data that didn't make sense. So this took probably around a year of me just hitting my head on the keyboard until I figured out how to do that magnetic conversion, because you have to go from CGS units to SI and do that with the giant magnetic coefficient, and that wasn't that trivial. So, but yeah, it's a really cool tool to then look at different diameter particles and look at the physics from there. So some of the applications, for instance, it could be for power electronics, for your transformers. It could be used for, there's some papers looking at it for semiconductor processing. So instead of doing UV photolithography, you could do RF photolithography and use particles to heat up and do a uniform cure. You can also, there's another paper looking at doing this to help melt snow on the road. So you can put these on the road and then use a microwave to help further heat up the snow and melt ice. So some interesting things there. People are also using them in order to help as contrast agents for magnetic resonance imaging for MRIs. Actually, what they use right now is very toxic. It's unbelievably toxic if you were to look at what they're using. But they go ahead and put these ligands around it so that it prevents it from bonding to anything in your body, and goes out through your urine. This is just iron oxide compared to that. Yeah, so yeah, there's ways of making things fairly safe. So And then this is a really cool part of the presentation. So never before has this been seen in the public before. This was actually all made at Johns Hopkins University Applied Physics Laboratory, and this was all 3D printed, what you're seeing here. This is a completely metal antenna, 3D printed, and it's also a shape memory alloy and can shape change. So I show this, I don't know how to do a video from this clicker. Will it? I probably have to go here. That's fine. So this is just our initial prototype, and we're still constantly developing this as we speak. So this is real time, and as you can see, this is a double spiral antenna going from a flat configuration to an extended conical, and then going back down. And you can keep doing that as many times as you want. And this is huge because what we're looking at is how can we extend the utility of antennas. So right now, you make an antenna, you're kind of stuck with that size or that configuration, or if you can shape change, it's due to using, say, bulky motors and having non-ideal surfaces you have to work with in order to change the shape. And we're not limited to double spiral antennas. This could be applied to any antenna you can imagine, which is the really cool part. So the whole purpose of doing this is, for instance, maybe I want to switch bands. I want to go from, say, K, X band, and I want to go all the way down to L band, or maybe even lower. Maybe I want to go to HF, all one antenna system, without having to have a whole nother separate antenna. So we can make everything a lot smaller. And then in addition to, we can change the directivity. So we can go from, say, the antenna having the beam pointed more straight towards something that you want to more omnidirectional. So that's the whole purpose of doing this. So yeah, in this test, this is a blow dryer and a cooler. And there are ways of doing this direct, so you don't have to use that. But yeah, no, you do not need to use a blow dryer in the final form, but it's more of a demonstration. But that's the incredible part, is just through changes in the thermal properties of the antenna, this could actuate. There are no mechanical motors and such. And it's actually fairly sturdy. The initial versions are kind of like a slinky, but now they're actually like fairly hard. So once it gets to an actuated state, it's basically very firm. So yeah, and to model these, you can't really use papers. They're non-conformal. So that's where we heavily rely on computational electromagnetic software to understand how these work and optimize them. Because we're using this in a not normal way, best way to put it. So, yeah. Oh, so what's possible with the additive manufacturing aspect that you can't do normally? For instance, say you want to go something a little bit more complex in this geometry that you can't do by hand. In addition to, you have more control over if you want to put any other fine details. So this is just like our initial prototype, but there's other things that we're finding that we need to add in that would be fairly difficult to do by hand, and also scalability. So if we can just, once we have a reliable print method, we can go ahead and print hundreds, thousands of these out, or even millions, without having to worry about a 5-axis CNC mill trying to meticulously cut these out, and especially when you go smaller. This is, a proof of concept, but if we wanted to go to something that's like half a centimeter in size, that will be much harder to do with traditional manufacturing techniques. And you can't really just do photolithography. This is a moving antenna, so the material has to be made in such a way. Yeah. So, and presently, it's only been done here at APL. So, yeah. So this is around 2 to 3 inches in diameter that you're looking at. Yeah. So, yeah. And then going into more of the additive manufacturing aspects, and this is also the other point of looking into AM, is when you get to really small elements, to do that by hand can become very costly, time consuming. But if you can use AM, you can use traditional processes that are out there right now, and then be able to make your antennas faster, more affordable, and also the promise of making them, for instance, more repeatable, more accurate, and pushing limitations. So for instance, the DDOT antenna that I showed before for measuring high electric fields, we had a paper recently published in IEEE Sensors We went ahead and printed using complete additive manufacturing techniques a DDOT antenna. And what DDOT stands for is displacement dipole, comes from displacement fields. I'm not going to go into the whole details of that, but it's a way of measuring the electric field, and you're taking the derivative of that field, so the rate of change, and then that signal, you integrate that, and then you can get your E field. And the great thing about these, supposedly, all you have to do is take the equivalent surface area of this antenna, and that's your Cal factor. So that's what makes them really great. And it is based upon the diameter of this dipole. So for instance, when you want to get to like 10 gigahertz is right now like the present limitation. To go beyond that, you're trying to go from a dipole, or in this case is a ground DDOT, it's a monopole, but this free field version, so it's more of a dipole. But anyway, you're going from a couple millimeters in diameter. And to do that by hand, obviously that requires a lot of work. We can actually do this through additive manufacturing means, and then go from there. So obviously this is not shape changing. This is really, really cool. But this is also another practical implication of how AM is helping us. Yeah. And then just as a final slide, just kind of tying everything together. Basically, think deeply across all your disciplines. And the importance of understanding a little bit, let's say from aerospace, mechanical engineering, material science, is that a solution there that might have seemed to be only a solution for that particular field could potentially be useful for maybe a double E problem and such. And so you can make these connections all around. And then in addition, greater understanding of stakeholders. So for instance, my military background helps it make it much easier to understand what the warfighter needs and applying technologies towards that end. And you know, best marketing your ideas. So if you have the appreciation of the arts at least and understanding, you know, maybe what's the best lighting to showcase this product, get that ooh and ah factor. That helps a lot for your presentations. And this just kind of shows like the different things going on, like material science, design experiments, coding, applied physics. Other than the societal implications aspect, entrepreneurship is a big thing. I don't know if maybe we're starting like entrepreneurship, maybe classes or something, maybe double A, or maybe something, maybe more graduate level. Yeah. Okay. Yeah. It's definitely a great soft skill to have. Is how do you pitch, for instance, when I was in the Air Force, the strain sensing paint stuff, I had to pitch, you know, these nanomaterial concepts in like 4 minutes to around 20 generals who may have no clue at all about the engineering aspects. So how to have a broad audience understand why it matters, how it applies to the stakeholders. That's very important. And so, yeah, that'll carry you far. And yeah, any questions? That concludes the whole presentation.
Right, are there any questions either here or in Zoom world online? Sure.
Correct. So for that, right, there's in this case, right, there's 2 different states for this one specifically, and that's based off the phase changes of the shape memory alloy. So you're going from one type of alloy phase to another phase, and that's all done by a temperature change. So that temperature change can actually be designed as well, where it would exactly change during the manufacturing process. So you could have it actuate right around near room temperature, or maybe a little bit further. Depends what you exactly want with it.
So on a related note, I think it was on slide 22 or so, where you had those 2 graphs of high field and data going a little off. Yeah, the one, thanks. I was just wondering how quickly, so basically you're looking at the response as a function of temperature. How quick, when you change temperature by say 1 degree, how quickly does it track? Or is there a long delay, or is it pretty much instantaneous in terms of response?
Are you saying in terms of the measurement from the electrooptic probe?
Yeah.
Oh, it's instant. So this is real time.
Okay, so it doesn't take time for it to actually track changes in temperature. It doesn't, it's instantaneous.
Right. Oh, so in terms of, I think what you're getting at, in terms of the temperature gradient going into that sensor, so we actually left it running for a whole day
Oh,
to get to
okay.
that temperature. So we have it, we know for sure it's at that temperature. I wasn't
I
like,
see, okay.
so once it's at that temperature, that will be that cal factor.
Right.
Yeah. So
Yes,
yeah.
because it brings in the question of what happens if you have fluctuation, or how well controlled is your temperature? What happens if you have excursions of any kind? If you have like a 0.01 degree C fluctuation either way, does that affect your response in any significant way?
Right. Well, if it, for instance, if it were to all of a sudden experience temperature and that whole crystal were to be, say, a whole degree higher,
right.
It would still be tracking with what this would be doing.
Okay.
But you know, for instance, you would need to integrate though a thermal probe right on your electro-optic crystal or really near it.
Okay.
And if you use some insulation around there, that can help it make it more consistent. But even with insulation, if you were to leave something out for a while,
right.
It can eventually go to that type of temperature.
Okay. Other questions?
On the EMRF, is the head lithium niobate waveguides or something?
For the specific one I was working with? Yep.
Yeah, I had a question, yeah.
So for these types, the lithium niobate, yes, there are, there's waveguides etched into it. And it basically works with as a Mach-Zehnder interferometer. So you split the beam, comes back, one leg is at a different length, they converge. You also have an electrically small antenna element on the one leg. Electric field. Right. So, and the fiber will go right back. So, and these can vary in technology. This is just using standard single mode fiber. This company actually figured out how to calibrate that fiber line in real time with the hardware in a loop. Some other companies, they use polarization maintaining fibers. It has become a lot more costly and stiff and such. So each company has their own little proprietary fiber technology.
And so basically what you're doing here is that, since you mentioned in comparison to conventional antennas where you're you need to actually change the configuration to get so here what you're leveraging are the electro-optic coefficients of that material. Just by applying a field, you're altering those.
Right, so like the index refraction will be changing.
Right.
Which changes your optical response.
Right. Yeah. So does that also give you a better way of doing, say, the equivalent of electronic beam steering with conventional antennas? Can you do it better with something?
So I was more doing this for along the lines of just sensing purposes.
Okay. Yeah.
So in terms of transmission, though, yeah, that one I'm not sure about.
Okay.
So yeah.
Topical research.
Yeah. But I did see there was a group, I believe in California, when it was IEEE sensors, where they were taking terahertz optical fields and going to an antenna and creating an RF response out of that.
Oh yeah.
But not sure where.
Yeah, we're kind of doing that somewhat. You can do, so you start with an optical signal and you interfere it with another optical signal and you get a beat signal that's actually in the RF. So you can actually generate RF with optical terahertz or millimeter wave.
I think that's like the way to go. I mean, optical and terahertz regime thing right there.
Cleaner signals. You don't have the electronic noise issues.
Yeah.
Right. Other questions at all?
Oh, sorry. Oh, for the strain sensing aspect? Yeah. Oh, so for this one, yeah, we actually bought for this experiment from NN Laboratories, and they provided a binder that works well with their quantum dots. So usually there's some type of like silicone-based type of binder, or it could be another type. But the main thing you have to make sure is the fluorescence of that polymer. So you don't want that to have a fluorescence that's on your signal too of your quantum dots, and also take energy away from your quantum dots as well. So I don't know the name of the exact polymer off the top of my head, but for these though, that actually is proprietary from the company. when I was doing this. But there are some design considerations. Yeah.
Enough to be, so the dots are embedded in the polymer. Something to the dots.
Yeah.
Wanted that person.
Yeah.
What's going on here?
So yeah, in terms of the actuation mechanisms, so when you're pulling on this, you can imagine you have like a system of these, right, floating around. It is known from fundamental theory that when you apply a strain directly on these dots, that can change their band gap, which therefore will change their emission. But that might only be like a couple nanometers, maybe a lot less. In terms of the main actuation mechanism, I think that would be from force of resonant energy transfer. So the crosstalk communication between the dots. So as you bring them further away from each other, that will change the amount of energy from one dot to the other, which can cause a shift in that optical response. That's, I think, maybe the main mechanism. It's a hypothesis. Yeah. But yeah, you can actually track it. I mean, that's the incredible part, is it does track well with stress strain curves once you apply a cal factor. So, and a $5 light, black light from Amazon. So, yeah.
What are your fluorescence lifetimes like on like order of magnitude?
Oh, for quantum dots, it depends drastically on who's making them and what they contain. But they're around nanoseconds and even less than that. It depends on what's on them and what material.
Right. Anything else? Well, if not, let's thank Dr. Sherburne again for a wonderful talk. Thanks very much.